Hello, class. As we get into this topic, the nature of science, the history of science, some philosophy of science, I wanted to start off with a scriptural reflection on kind of what science is, what we're doing when we do science. So the first verse I wanted to talk about was Acts 17, verses 24 through 28. It says, "The God who made the world and everything in it, he who is Lord of heaven and earth, does not live in shrines made by human hands, nor is he served by human hands as though he needed anything, since he himself gives to all mortals life and breath and all things. From one he made all nations to inhabit the whole earth, and he allotted the times of their existence and the boundaries of the places where they would live, so that they would search for God and perhaps grope for him and find him, though indeed he is not far from each one of us. For in him we live and move and have our being." And I like this verse. I think that it helps us to remember that God is both transcendent and immanent, that God is above everything, infinite, and that's what transcendent means, and God is also immanent. God is there, closer to us than anything else, and within and moving within everything. So when we do science, we're really investigating things that God has made, things that God's mind came up with, and learning more about God. So in that way, Dr. Eiler likes to say that scientists are priests. And there's a verse in Proverbs 25 that says it's the glory of God to conceal things and the glory of kings to reveal them. So in that way, scientists are kings. So scientists are both priests and kings, at least in one way. And when we look at science, when we do science, we're really doing something sacred. We're using the intelligence that God has given us to understand things about God's creation. And I think it's a good thing to keep that in mind as we move forward in trying to understand what science does, what it's useful for, and how it can help us further our own Christian faith. So when looking at science, we can start at the beginning. You're probably familiar, at least a little bit, with the scientific method. And in this, we have a hypothesis, an educated guess about the solution to a problem, then do experiments. We analyze those experiments and come to some sort of conclusion. So this is sort of the basic outline of science. It's doing some sort of empirical research and then using that empirical research to either confirm or deny certain hypotheses. And the really important thing about science is that science makes predictions. So those predictions can be about laboratory experiments. They can also be about the sorts of things that we'll find out in the world, out in the universe. But that's the important part, that a good scientific theory is going to make some sort of testable prediction, and then scientists will go out and see whether that prediction is true or false. That's sort of the fundamental part of science. So here I'm going to present 3 definitions that I think will be helpful when moving forward. First is the definition of science. I would define science as a theoretical discipline that attempts to understand the natural world through objective, empirical means, and that the purpose of science is to find a systematic and coherent understanding of nature. And science does that, attempts to accomplish that purpose via scientific theories. Scientific theory is a collection of testable ideas that is used to make sense of or explain some aspect of the natural world. So we're going to look a little more in depth at some of these particular words in these definitions. But it's important to note that science is dealing with the physical, that it's limited to the physical, and that it's primarily concerned with theories that are attempting to explain aspects of the world that we observe around us. And a quick note on theories. Theory, sort of in common usage, just means like my best guess or something along those lines. But in science, scientific theory is something that's more concrete, that has been tested, that is widely accepted. For example, gravity is referred to as a theory. There's a theory that light travels at the same rate. Things that essentially everyone accepts about the world. So certainly theories can be wrong, but it's not a legitimate sort of attack on something to say, oh, that's just a theory. You might be able to say that about your friend's ideas or your crazy uncle's ideas or whatever. But when it comes to scientific theories, we're dealing with something that has been tested and generally accepted in the scientific community. This will become important when it comes to things like the Big Bang and evolution. Certainly there are ways of objecting to those theories, but merely the fact that they're a theory is not a hit against them. Alright, so here we're going to take a closer look at 4 of the words I used in those definitions to hopefully flesh out those definitions a little bit further. First, say that science is theoretical. And when I say that, I mean that it's concerned with theories, those scientific theories, and that it's trying to understand nature in a general way. So what science wants to do is discover laws, form theories that we can use to then deduce things about specific situations that we encounter in the world. So the more general, the more applicable a theory is, the better. Science also attempts to be objective or free from bias, and it does so in 2 main ways. First is peer review. When a scientist comes out with some idea, a bunch of other scientists then go and try and repeat the experiment, and they do the experiment in different contexts, in different places, and sometimes in different ways, to try and make sure that what they said is the case. So when scientific results come out there, when you hear people talking about scientific facts or things that have been proved by science, usually what they mean is that it has been subjected to peer review, and as far as we can tell, it is the case. No one has been able to disprove it yet. Another way that science attempts to be objective is through the use of mathematics. Numbers are not really open to human bias, so by using mathematics in scientific theories, they're attempting to sort of cut out the human element and keep it as objective as possible. Science is also empirical, and that just means that it's dealing with the physical, that it's limited to the physical, and while scientists often will make metaphysical claims or things that are beyond the physical. We'll see this when we take a closer look at the new atheists, for example. Science really only can talk about the physical. That's its realm of expertise, and outside of that, it's not able to give us good information, or really any information. Lastly, science is attempting to be coherent. Meaning that it doesn't contradict itself, that you can accept everything without needing to go to this double think, needing to think that something is true in one area but false in another. So that attempt to create sort of a unified system of thought. Now that we hopefully have some idea of what science is, what it's up to, I'm going to talk about some assumptions that science needs to make in order to do what it's trying to do. So science doesn't just follow logically from first principles. Science isn't just obviously the case. You need certain things to get going. Then science is great great at its job, but you need these things before you can even begin the scientific project. So the first thing you need is uniformity. So when I say uniformity, I mean that it needs to be the same both in time and space. So science assumes that over time experiments won't change, that the laws of nature stay the same, and that it doesn't matter where you are in the universe. For example, scientists assume that the gravitational constant is universal, that the speed of light is universal. There's no way that we can confirm this, but it is a part of the scientific endeavor that that's the case. The second assumption of science is intelligibility. That there actually are these laws out there that we can go out and discover, that our minds map onto those laws in some way. So it may well be the case, or at least could have been the case, that the universe wasn't governed by laws, that it was just random occurrences happening, but it certainly seems as though we live in a universe that's governed by laws, and that's something that science needs in order to do its job. A third assumption that science makes is that observation allows us to infer things so that we can go from what we can observe to what we can't. We can't observe a lot of things because they're far away, because they're too small, too big. So we need to infer things about them based on what we can observe. And science needs that assumption in order to kind of make their general theories try and make sense out of the whole of the physical world, since we can't observe all of the physical world. And the last assumption, at least that I'll talk about in this video, is that our senses are accurate. So if our observations are fundamentally flawed in some way, if our senses don't map onto the world, or if our brain somehow fundamentally distorts the information that our senses are giving us, science becomes impossible. So without these four things, among others, science can't do anything. You need to just assume that these things are true if you want to do science. And I'll say more about this later when we get to next week, but I would want to argue that a God who is intelligent, who created the world, makes more sense out of these assumptions than out of a world that just sort of popped into existence or always has been in existence. I don't see a good explanation for why that sort of world would be intelligible, would be governed by laws, etc. But more on that at a later date. Another important thing to note about science is that scientific theories are fundamentally underdetermined, meaning that they do not follow directly from the data that we're able to observe or gather in various ways. So there will always be more than one theory that fits the data, and scientists then need to choose the theory that best works or that they think will lead to the best results. But it's not the case that scientists go out into the world, gather data, and then a theory appears. A theory needs to be constructed by people, and often throughout the history of science they're wrong about the theory that works best. So we need to know that scientific theories are never 100% proven. They're always up for debate. They're always able to be disproven at some point in the future. Since scientific theories are underdetermined, scientists need to use various criteria to determine which theory they think will work best to explain the data available to them. And the two main criteria that are used by scientists today are simplicity and explanatory power. So simplicity just means that it is requiring the least amount of presuppositions, or the least amount of statements. So to give a fairly simple example of simplicity, if we had a graph like this, most of us, if we wanted to connect all the dots, would do something like a sine wave or a cosine wave, but that need not be the case. We could connect all the dots with some roundabout way like this. So while scientists value simplicity nowadays, it need not be the case that the most simple theory is the correct one. Scientists are also concerned with explanatory power, the ability to be more general, to apply in more situations. Since they're trying to explain the whole of the natural world, more explanatory power is better. But again, it need not be the case that the theory with more explanatory power is correct. And if you've heard scientists talk, you may have heard them talk about beauty in science or beauty in equations. And what they mean by that, if they say that a particular theory is beautiful, they tend to mean that it is both simple and it has a lot of explanatory power. So to illustrate this, pause this video and go to the video that I have below of Frank Wilczek, who helped to discover something about the strong nuclear force. So pause this and then come back after you're done watching that video. As you can see, what led to his discovery, what led to that theory that's now widely accepted, is the fact that he followed the beauty in the equations. He just thought, this is too beautiful to not be true. And this is not an isolated belief in scientists, it's actually very common. So two other examples of scientists who sort of followed beauty to find something that ended up being true, as far as we know. One is Murray Gell-Mann, another Nobel laureate, and he was working on the weak nuclear force. He said 3 or 4 of us in 1957 put forward a partially complete theory of the weak force in disagreement with the results of 7 experiments. It was beautiful, so we dared to publish it, believing that all of those experiments must be wrong. In fact, they were all wrong. So in this case, he went against experimental data because he was following the beauty that he found, and he ended up being right. Paul Dirac, another famous physicist, one of the people who helped in the quantum revolution, said it is more important to have beauty in one's equations than to have them fit experiment. And when talking about some of his work, he said the result is too beautiful to be false. So again, this idea that beauty leads to truth in some way. And I think that this, again, is an argument for a designer, an argument for God, because in a universe without God, there's no reason that beauty would need to sort of lead one to truth. And in fact, great minds have really puzzled over this. One of Einstein's quotes is that the most incomprehensible thing about the universe is that it is comprehensible. So he's just reflecting on the fact that we needn't to be able to discover things about the universe. It could be the case that the universe was totally inaccessible to us, but for some reason we can discover things about the universe, and there seems to be this order, this underlying beauty to the universe, and that, in my mind, points to the existence of God, of a designer. So again, we'll talk about this more in the future, but this is just an introduction to science, how it works, what it's trying to do, and how scientists are picking those theories that they end up supporting.